Thanks for joining us at Apache Apex Big Data World. And I'll introduce myself. I'm Apache Apex PMC member. I'm also a lead engineer at DataTorrent. My background comes mostly before joining DataTorrent. I was doing proprietary software, interested in the middle tier, doing a lot of LAP development. And I am Call of Duty fan, so when I'm not coding, I play games. So today, I'll cover two applications that we use to benchmark Apache Apex. One is used specifically to benchmark platform itself, and another is a reference at tech reference application that covers an actual use case or mimics an actual use case. We developed at Apex, right, at DataTorrent, we developed an application that is used specifically to benchmark engine. It is important, right, so that we can compare throughput and latency across various releases to play how size of a tuple impacts throughput and how it impacts latency, to compare what is the impact of various stream localities that Apex support, how that impacts throughput, and also how we can adjust and how we can select various default parameters, attributes in terms of in terms of Apache Apex. For example, what is the optimal queue size to use? What is the optimal buffer size in network communication to use? And we can come up with the most optimal values so that application developers are free from making those choices. We also use that application to benchmark stream codecs. And additionally, it allows us to understand impact of garbage collection on application performance, or I would say it's more on a platform performance, right? So it's how garbage collection, whether there is any impact, or it's how JVM handles garbage collection within containers. So this is an application that we use. It's quite simple, right? Basically what we have is we have one operator that emits a byte array. It is it's a byte array of a fixed size, so it's not hard-coded. Operator allows to change size of that byte array, and later I'll show how lengths of emitted tuples, how it affects throughput, and whether there is any impact on the latency. Also that operator allows to emit based on a property whether has the same byte array always, or for every tuple to allocate a new byte array. Note that this is specifically used to benchmark an application. Don't do that in your actual application. There is a reason for that, right? Once a tuple is emitted by an operator, it is put into port sync, and port sync can hold to that object for some time. So if you're modifying that object before emitting a new one, like basically what you already emitted will be also modified. So this technique is only used to benchmark and understand impact of garbage collection on the performance, but please don't use the same in your application when you design your applications. And the second operator is a counter. It basically counts how many byte arrays an operator received within a window. And those two operators are connected by generator to counter stream. And we can change or we can specify various stream localities to be used within an application. So we can basically compare how various stream localities impact throughput and latency. So we run this application on our development cluster. It is 13 nodes Hadoop cluster that runs Cloudera distribution 5.4.9, Hadoop 2.6. With each node, it is Xeon, like a 2.3 gigahertz processor. So basically, it brings total number of CPU with hyper-threading to 24. We have every node has 6 hard drives with 3 terabytes, but for running that particular application, it's not that much important. And cluster, nodes on the cluster are connected by 10 gigabit Ethernet network. That's quite important because, when we go for no locality, right? Once we have operators connected over network, network speed makes a significant impact. So we want to see whether we can saturate network or whether network is a bottleneck. So this is a result of running that application on 2 versions of Apache Apex, right? And this is pretty much there is no partitioning, there is no shuffling involved, and it's basically what thread local means. It's a function call, right? It's one operator immediately calls the next function. The results are really interesting, right? We basically what thread local can achieve. If there is no without garbage collection, we can go into 60 million tuples per second emitted. And for 64 byte array lengths, right? Once we introduce garbage collection, that throughput drops to about 40 million events per second. But once length of byte array increases, and we use byte array just to emulate, right? It's basically maybe an actual payload may not be a byte array, but considered what impact it has on platform performance from 40 million tuples per second, kicking in garbage collection reduces that to about 1 million event per second. While if we emit the same array, right? In case garbage collection doesn't kick in, it's throughput keeps the same, and it stays flat at about 75. It's 60 million events tuples per second. But there is definitely problem with thread local, right? Like basically, if two operators are CPU intensive, thread local is not a good choice. So the next choice, like from throughput performance, will be container local, right? Like in which case, operator will still reside in the same container and will be connected by a queue between them. Like there is a cost now for synchronizing and accessing that queue, and performance throughput now drops to like about like 4 or 5 million tuples per second. Like in the later release, we have optimization where, like for the same container local, we can achieve about 12 million events per second by using a special queue mechanism. So that like makes container local quite a good choice like for you to consider. It's like when shuffling is not required and when a single node have enough power, enough CPU power. And this is the result for when those two operators resides on different like in different containers, so it's like in different nodes, right? So now network kicks in. Not only network kicks in, now Apex also need to do serialization when it emits tuple and deserialization like on the other part, right? So like basically now stream codec kicks in, and once network and stream codecs or serialization plays role, you can see that impact of garbage collection is not so significant, right? But throughput drops almost to 1 million events per second. So that covered an applications that we use to benchmark platform itself. And now I move towards an applications that we use to compare various streaming engines, and that application was initially developed by Yahoo, and it simulates a use case in ad tech. Right, so basically an event comes from Kafka. It comes in the form of a JSON object. That JSON object needs to be parsed. Then some records needs to be filtered out. It's application may not be interested in all events published to Kafka. Then that object may need to be enriched, for example, by lookup from an external database, and then there is some window operation or aggregation operators that needs to be performed, and result written to an external database. So Yahoo did performed a benchmark, right? And this is the parameters that they used. Not, I would say it's not very impressive, right? It's a reference application, but I think in general, it's on the lower side. Not that many campaigns, not that many ads. Number of events is not significant. They basically run it between 50,000 to a maximum load of 170,000 events per second, right? It's like, where it's like in the previous example, we saw that it's like in general, Apex can handle millions of events. So this is the result. It's like published by Yahoo. It's like they compared Spark streaming with Storm with Flink. It's like it's like for me it's on the right. For you it's on the left, right? It's basically it's a latency for it's like arriving events. It's like with like the largest latencies goes like in like I believe in the minutes range, and on the right side it's like again like a latency, but for various loads. So as you can see, Spark streaming like can handle like a load, but like from a latency point of view, this is what you would expect from a micro-batch system. Like for the load that Yahoo used, like Flink and Storm were able to handle the workload with like a good latency. Later, like developers from Flink showed that like once load is increased, Storm is not able to keep up, but Flink can handle millions of tuples. So after that paper was published, it's like after that blog was published, we decided to try to add Apex to the picture and see like what Apex can do, and designed Apex applications that will handle that EdTech use case. And this is the result. Like you can see, it's like basically both Apex and Flink can handle the workload. It's like what we managed to do is on that cluster to load both Flink and Apex up to 3 million events. It's like with 20 Kafka brokers, and it's like the same number of parallel pipelines that Apex and Flink handled. There is a slight increase in Flink in the latency, but basically that comes from Kafka. Kafka is not able to deliver events to a streaming platform without introducing latency into the events. So at this point, I think from a reference application, streaming platform definitely can handle that case. Well, that pretty much covers both applications that I wanted to introduce. Any questions? There are other benchmarks that we're running for operators themselves, but this is more for a lot of those benchmarks depends on on an integration, how if you're doing that for JDBC, what is their it's like a database we use. If that's like Kafka, that also impacts Kafka operator, right? So most of the time, it's like benchmarking in streaming is yet to be defined. I think it's like there is an attempt that was done by Yahoo, but it covers only one use case or one verticals. And I think that like as there is more and more interest like in the community for streaming application, we'll see more benchmark coming.